Welcome back to the Hebrew University NMR laboratory. We have decided at the Hebrew University to recycle the helium that we used to cool our NMR magnets. This is because of price increases, supply security, and to conserve a non-renewable resource. The NMR magnets need to be kept at extremely low temperatures to maintain their superconductive properties. Helium is used because it has the lowest boiling point of any material at 4.2 Kelvin. The magnet must be submerged in liquid helium without fail at all times, otherwise superconductivity will be lost. This can damage the magnet in addition to the fact that recharging a magnet is very expensive. Therefore, it is imperative to have a reliable and affordable supply of liquid helium. The USA stockpiled helium for most of the 20th century because it had military applications. First in airships, then for cooling rocket engines. Due to lower demand for military use, the US government decided in 1996 to gradually sell off its reserves over a 20 to 25 year period. At the same time, demand for helium was rising due to the popularity of liquid helium-cooled MRI and NMR instruments, and relied on the cheap supply of helium. In the meantime, the Russian company Gazprom increased its production and sale of helium. However, following a number of technical failures in 2021, the war with the Ukraine in 2022 delayed their production of helium at the same time as the US reserve supply was running out, and their crude helium enrichment unit suffered a technical failure for several months. Today, the helium supply has become more reliable, but at a much higher price. The price of helium has quadrupled in the last few years from 60 shekels to over 240 shekels per liter of liquid. Helium is obtained as a byproduct of fossil fuels with concentrations up to 7%. It is therefore non-renewable. The atmosphere contains 5.22 ppm of helium. While this escapes into space, it does so very slowly over tens of millions of years. Extracting helium from the air would effectively be renewable because it is returned to the air after use. However, the price would be about 8 times higher, or 2,000 shekels per liter of liquid, than even the exorbitant current market price. Security of the helium supply is a critical factor. The USA and Russia remain the major suppliers of helium. Only a small fraction of the world's production comes from other countries. Any problem arising in a major supplier, such as in 2022, when both major suppliers were compromised, can disrupt the helium supply. In addition, there is always a risk of boycotts from political considerations. Recycling and maintaining a local reserve of helium can ensure that we will not run out in a crisis. With all this in mind, we took the strategic decision to go for helium recycling. The current move of the Students' Lab NMR spectrometer to a building near our Cryogenics department gave us an opportunity to try out helium recycling with the intention of applying the experience gained to a recycling system for our main NMR lab that is further away. A helium recovery system consists of a connection to the source, storage in sacks at low pressure, compression, purification and liquefaction. We had to build the system quickly before the installation of the spectrometer in the new site, so had to make shortcuts just to get it working. The source of helium is an NMR magnet. This must be kept at 4.2 Kelvin, otherwise the magnet will lose superconductivity and quench. The boiling point of helium increases by about 0.12 Kelvin with every 100 millibar of pressure, so any recovery system must minimize back pressure. To prevent problems, an overpressure relief valve is needed. The helium leaves the magnet via a one-way valve and goes through a gas meter and pipework to collection bags. The system must be well sealed because helium escapes very easily. The diffusion rate of helium is 2.7 times greater than that of air. Helium even diffuses through glass. To prevent leaks, the pipework is made of copper and welded. The installation of the pipework and connection to the existing line was carried out by Bachuri Building Limited under the management of Itsik Cohen. He installed the system, connecting it to the existing line. He used 1 1/8 inch copper piping and helium-rated ball valves. And yes, we use inches to measure pipe diameters even in Israel. The inner diameter of this piping is nominally 0.997 inch. The piping was welded and the ball valves and gas meter connected with Teflon tape. The connection to the magnet is via a stainless steel bellows. Had the building vibration been a problem, the magnet could have been connected via a nipple between fills using flexible silicone tubing. Connections to valves and the gas meter are carefully tightened with Teflon tape. After installation, the system was pressurized to 5 bar of air, and all the connections are checked with soap and water. The line was left pressurized for several hours to check for leaks. It took a few attempts to get the leak rate to an undetectable level of 1 milliliter per minute for 35 liters of gas. The collection bags are connected to a compressor that activates when they fill up. The compressed gas is stored in cylinders at a pressure of 200 bar, ready for purification and liquefaction. The helium gas is filtered to remove water, then oil, and compressed to between 8.5 and 13 bar. It is then cooled by expansion while driving a turbine, followed by further expansion and cooling in a heat exchanger. This is called the cloud process. The first stage cools the gas to around 50 Kelvin, precipitating out any air as a solid. The solid is then warmed up and purged. The second stage of the cooling reaches around 11 Kelvin, which then expands to precipitate liquid helium and recycles gas to the heat exchanger. The process also produces purified helium gas that is stored in a buffer and recycled. From the chiller, the liquid helium is transferred to a 1,000-liter holding tank ready to transfer to mobile dewars for distribution. Before filling, the mobile dewars are pre-cooled with liquid nitrogen. The condensed liquid is then siphoned out and the dewar flushed with helium gas to remove nitrogen before cooling with liquid helium. On cooling the NMR magnet, the flow rate peaked at 50 meters cubed per hour and the sacks filled up. The compressor is rated for 25 meters cubed per hour, so we had to dump about half the excess helium into the air. A routine helium fill produces much less gas, 4 meters cubed per hour, and between fills, the rate is about 0.012 meter cubed per hour. This may be insufficient to register on the gas meter, or there may be a leak, although no leak could be detected. There are a number of shortcomings in this first attempt at a helium recovery system that has been installed that can be addressed by reference to systems elsewhere. For this reason, I visited the Weizmann Institute. There they recycle about 80,000 liters of liquid helium per year, compared with 3,000 liters that the Safra campus of the Hebrew University uses. Each installation is attached to a programmable logic controller, PLC, that monitors and controls the helium sent for recycling. On each line there is a check valve set to 50 millibar to prevent overpressure on the magnets. The check valve that we installed was cheap and may be leaking. The helium arriving from the installation is monitored for oxygen impurities that indicate contamination with air. If the level of oxygen is greater than 0.4%, indicating 2% air, the input valve to the gas meter is closed and a valve open to dump the gas into the air. There is a transparent tube containing a ball that gives a visual indication of flow and a manual valve to bypass the meter in case it needs to be removed. For a collection point far from the Cryogenics department, the gas goes to helium sacks. When the sacks are full, a valve is opened and the helium pumped with a blower to the Cryogenics department. At Weizmann, this is a distance of 1.5 kilometers, and the pipe diameter is 2.5 inches. At the receiving end, at the Cryogenics department, the gas is again tested for oxygen and passed through another meter, or, if contaminated, dumped to the air. In the case of the Student Lab 300 MHz NMR spectrometer, the distance is about 47 meters, so no blower or helium sacks are necessary next to the lab. However, the system should be upgraded with a PLC that controls the valves and is connected to pressure and oxygen sensors and a smart gas meter. A vent to air must be provided in case the helium is contaminated. At the Cryogenics department, a second meter and oxygen sensor needs to be installed and attached to their PLC. The proposed recycling system from the NMR lab is about 300 meters from the Cryogenics department. On each NMR instrument, there will need to be a separate check valve, connection valve, and pressure transducer. One gas meter and oxygen sensor and PLC are needed for the whole lab, and likewise at the receiving end at the Cryogenics department. However, due to the distance, there will need to be gas bags and a blower pump. A pipe diameter to Cryogenics of 2 inches will probably be sufficient. In summary, we have started the important process of setting up helium recycling to reduce costs and save non-renewable resources. As we progress, we hope to be able to recover about 85% of the helium that our NMR systems use. I hope you enjoyed this video and learned more about the NMR lab at the Hebrew University. The NMR lab is a world-class facility that offers cutting-edge research and services in the field of chemistry. The lab has a variety of NMR spectrometers that provide high-resolution structural and dynamic information on molecules and materials. The lab also has a team of highly experienced and friendly staff who can assist you with your NMR needs, from sample preparation to data analysis. If you are interested in using the services of the NMR lab, please visit our website or contact us by email or phone. Thank you for watching, and don't forget to subscribe to our channel for more videos about the Hebrew University NMR laboratory. See you next time.